Okay. So for today's lecture, we'll talk about adversarial robustness in deep learning. So we've heard a lot of story about the success of machine learning, right? In particular, deep learning. So for image classification, we are constantly, kind of improving the classification accuracy on ImageNet benchmark, right? So we're also very good at machine translation, and the AI or machine learning algorithm is able to outperform a human player at the Go game. And recently we have this chat GPT is attract a lot of attention and hypes, right? So we can do this kind of dialogue with the machine learning engine. So we are able to get very realistic response, get the accurate information from chat GPT. So it seems like there's a clarity of the success of machine learning. But the question is machine learning, algorithm truly ready for real world deployment, right? So in the supervised training paradigm, right, we all know we have a training data set and we can train the model, and we using some validation set to validate, right, if the performance is able to generalize well. But in the reality, right, so the real world deployment, the data distribution can be very different as compared to the training data, right? So the performance, the high performance on the training data set may not be translated into the high performance on the test set because of the data distribution and also some of the adversarial or malicious attack can be existed in the real world deployment situation. And here are some of the examples. This malicious attack on machine learning models. So some of the trained models can fail dramatically in terms of the performance. And here is an example during the image classification. I think maybe the text on this image may be a little bit too small. You're not able to see this correctly. But basically, this is the image of the washer. And when we take a photo or maybe we print out, and now the machine learning model is not able to correctly classify this is a washer. So we'll classify other different objects like safe or maybe speakers or other type of objects. And in this example here, if we look at the top row, right, so these people are wearing a particular designed glass, right? So we have this kind of patterns. So originally, the machine learning model without, if the person here doesn't wear this glass, is able to correctly identify the identity of each individual. But when wear this particular glass, so the machine learning model will falsely identify a different person, right? So for this one, it will actually predict at a high accuracy a totally different person. This is also the case. And here on this example, this is a toy turtle, right? So for this particular pattern on the shell, if you can see, there's some specific color patterns, right? So actually make the machine learning model fail, like predict a high confidence of this is a rifle. So definitely, for a human, right? So we definitely will not classify this is a rifle object. Okay, so this is another case for the stop sign. If we add in some of the perturbation in the image, right? So these white or black bars here. So this will also make the machine learning model fail to recognize this is a stop sign. Okay, so basically, these example says that the machine learning model can be brittle, right? In some of the real world applications, make some small changes to the input. The classification can make mistakes. Okay. So the adversarial attack is a technique tries to fool the machine learning models with some deceptive data, and is a growing threat in AI and the machine learning research community, right? So for simply put, right, so we have for image classification as an example, right? So we have this data and we train a machine learning model. So in this case, maybe the deep neural network. So we are able to, train the model to recognize this particular object correctly, right? So this is gonna be confirmed with the human perception, right? So we all recognize this as a macaw image, okay? But for the adversarial attack, right? So the idea is that we adding some perturbation to the original image, okay? And we generate this adversarial example, okay? So in this case, you can see that there's not much difference between this adversarial example and the original image, right? So at least from the human eye, we are not able to perceive there's going to be a significant difference. So in this case, human still is able to recognize at high confidence this is a macaw image, but for the trained deep neural network before, it will mistakenly recognize this image as a bookcase. Okay, so this is called adversarial attack, right? Trying to adding some of the perturbation to the image to make them train the machine learning model fail. So why we can do this, or why does this adversarial example exist? So if we look at a simple example, right? So we do this binary classification in this example, and we're assuming two classes, right? So class A and a class B. And if we do a classification, right? So we have a classifier or this boundary to separate these two classes, right? So if you look closely, in this particular example, there's a couple of data points, right, which lie very close to the decision boundary, right? Maybe this particular data point, right, and this particular data point right here is very close to the decision boundary, right? If we add a small perturbation, let's look at this one, the red circle here. If we add a small perturbation or some small value to the data, right, there's a high chance, right? So these small perturbation may make this data point move or shift over to the other side of the decision boundary, right? So we'll misclassify to a different class, right? So, but you may say that, okay, maybe it's just not the classifier, the decision boundary is not good enough, right? That's also possible, but in very complex cases, right, this kind of data points is inevitable, right? So if you want to maximize the classification accuracy, then some of the cases or some of the data points may lie very close to the decision boundary. Then in such cases, if we add in small perturbation to the data and the label flip or the misclassification can happen, okay? And also we can easily generate some adversarial examples to fool the classifier, right? So here are a couple of examples. If you look at this particular image, right? So this is, if we feed this data, this particular image to an image classifier, which may be trained on ImageNet, it will classify this as a baseball image. Well, we cannot say it doesn't make any sense because this pattern, right, resembles some of the patterns of the baseball, right? The stitches and, there are some lines may have some red color. And another example, right, this remote control, right? So there are some, patterns that resemble the button, right? So for the machine learning algorithm, it will look into this image and look for some patterns that assign a label that is closely or fit this kind of pattern, right? But for a human, we'll definitely not say this is a baseball, this is a remote control, right? So these can be considered adversarial examples that can make the prediction maybe not make sense, for a human. And there's also adversarial examples that we can, purposely created, right? So basically, these adversarial samples or examples that are similar to the data in the true distribution, but is able to fool a classifier, right? To fool the classifier to misclassify its correct label. So this is a modified version of the clean image that can intentionally perturbate by adding noise to confuse a machine learning system. So here is an example, right? So we have a input image, right? This is a panda image, and we can adding some of the noise or perturbation. So this is carefully crafted, right? The noise or design the noise. And when we combine this original image and this noise, and we using this generated image and feed it to the machine learning model, and now the machine learning model will give a totally different answer and probably the wrong answer, right? So this is the adversarial examples can be generated by adding the adversarial noise. And so these examples we kind of provided basically, in the digital world, right? So we have images, we adding some noise, and we feed that into the machine learning model. But is this going to be successful in the real world scenario, right? So how about in the physical world, right? Is it possible to generate adversarial examples or samples in the physical world, right? So, and the answer is yes. So we can generate adversarial attack in physical world. So in this case, on the left is the original stop sign, and on the right is the adversarial attack, right? So the attack may be, this kind of oil painting, or maybe a particular sticker put onto this stop sign. Okay, so if there's a machine learning model, or maybe this is the machine learning model deployed on the autonomous driving vehicle, right? So take the camera capture this image again and trying to recognize what this object or what kind of sign is in this image. And with this kind of adversarial attack, right, the stickers or maybe this kind of paint, it will no longer recognize this as a stop sign, right? Will be recognized totally different, right? Maybe just speed limit, right? And you can see how dangerous this can be, right? If it's autonomous driving vehicle, then when go through this, stop sign will just, keep cruising across the road, right? So there may be accident happen. Yeah, so for this case, right, so if we have this physical adversarial attack, right, so this, self-driving car may be recognized as just a speed limit or some other signs, not the stop sign. In the healthcare or medical domain, we can also do this kind of adversarial attack, right? So the attacker can alter some of the medical scans to remove existing or maybe medical conditions, right? The tumors, or maybe injecting non-existing nodules or tumors to the scan, right? So when the radiologist or physician to look at these medical image scans, then they will make the false diagnosis, right? Maybe the patient do have some type of disease or tumor, unfortunately, but because of the adversarial attack, right, tampering these medical scans, then the radiologist maybe make a false diagnosis or vice versa. So here is this paper, CT-GAN, malicious tampering of 3D medical imagery using deep learning. So they're using a GAN approach to tamper the 3D medical image scans to either injecting some of the nodules in the original scan, or either, or maybe remove some of the nodules in the original scan to tampering the image. So they show a very cool video demo. So how they are able to gradually changing those medical scans. So let's take a look. Okay, so you can see that in this demo video, right? So they have provided two cases, either injecting some of the nodules that was not exist in the original scan. The other case is remove some of the cancerous region, right? So, and they do this in this kind of 3D volume of the CT scans. So it's not just image classification, right? So we can add in the noise so that the machine learning model can fail on the image classification task. And we can add in these adversarial perturbations to examples and for other computer vision tasks, such as semantic segmentation and object detection, right? So for this particular example, if we were doing the segmentation, right, there are 3 dogs in this image. So as you can see here, if we're using the original image, this is the segmentation map, and this is the object detection outcome, right? So for semantic segmentation, right, we have the same label for the 3 dogs, right, because they belong to the same category. And for the object detection, you can see that they have 3 bounding boxes, and they all, classify this is a dog class. Okay, so after we adding these adversarial noise to the original image, and this is the segmentation output, right? So the color of the semantic map have been changed, right? So this will probably misclassify to a different category. And here, the bounding box for object detection was also changed, right? So you no longer see the output as a dog, but have different categories and with different sizes. Okay. So we can not just doing the adversarial attack on image, right? So we can also do this for other type of signals, right? Like audio or translation. So here, this is the speech, right? We can add in some of the perturbation. Now, if we're doing speech recognition, right, so they will totally output some random sentence, right, basically some garbage, right? So make the machine learning model fail to do the accurate speech recognition.